Okay, we have the mystery of why this thing doesn't work. Okay, well, it's actually fairly easy to solve that mystery. The easiest way to solve it is do things carefully when you first do them, which I didn't here. I did one silly little thing that I could not spot. And that silly little thing was when I did the integral p dx, I was treating p as your x component. So my p dx is here, and I used this for my p in order to get this, which isn't correct. Also, I didn't, in the integration, should have had a 12 down here because, no, actually, that should be a 10. Okay, because when I'm integrating like a u to the 5th, I get a u to the 6th over 6, and it should be 12. What's the matter with me? Would have been so much neater if I'd have just left it. Okay, anyhow, that doesn't matter. It still doesn't give us a good result. Although, yeah, you're still going to get 0. Okay, that's because I was doing the wrong thing. Now, trace over here. If I'm moving in this direction, my dx is negative. Moving in this direction, my dx is negative. And if I do x dx, my cosine cubed of t is always positive. Okay. So if I'm doing my p dx, anyhow, if you trace the signs of the dr, the tangent increments along the curve, and the signs of the sines and cosines, you don't end up with 0. And I couldn't reconcile this. Okay, just visualizing out down to the grady detail here. So finally, I broke down and wrote the whole thing in terms of the r vector, x of ti plus y of tj, with x of t and y of t respectively equal to the cube of the cosine, the cube of the sine. So the dr is dxi plus dyj, which equals this, which is totally consistent with what I have here. And then I wrote p equals, started to write negative x over 2, but no, it's negative y over 2. And that's negative sine cubed t over 2. And q is x over 2. Cosine cubed, that cube kind of got smudged, cosine cubed of t over 2. Then I wrote out the integral, and lo and behold, I got something different. Well, I saw it before I wrote it out, because I'd been using the treating p as if it was the cosine. Okay, now x is the cosine cubed on the parameterization of the curve, but p is not x. Okay, p is the coefficient of I in the function that you're integrating, and the function that you're integrating in this case is x over p equals negative y over 2 and q equals x over 2. So I was putting the x component in as if p was the x component, and that was totally wrong. Put it in like this, and you get an integral for which every term, well, both of the terms, are always positive because you always have even powers. Now, the fact that you have even powers, then I kind of welcome the odd power here with the sign left over because it was easy to do the substitution. You're going to have to do a double angle formula substitution here. Express cosine squared in terms of cosines and or sines of 2t. But you can do that. So I haven't gone through the details of the integration. I'm getting a little tired of this problem, to be honest. Not really, because when something goes wrong, there's a chance to learn something or fix something. Now I should not have to fix things at this stage. Haven't done this a million times. I don't think I've ever done this one. Who knows? But right there is the integral I think you end up with. And you can complete the integral if you wish and compare it with my estimate of the area here, or compare it with your own estimate of how this area would compare. So that's kind of it. Incidentally, if you're doing the direct area integral, you could do a polar integral. I think it'd be a little bit nasty. But you could do, you could parameterize these arcs in terms of theta, getting your R in terms of theta. Be a little messy, but it would also be an interesting thing to try and to learn something from. Yeah, I'm just going to include this other. No, this other thing's important. I'm going to do a separate video.